So this week in statistics, we're going to play around with inferential statistics, which is making predictions and testing things we believe to be fact about populations. Start off with proportions here and the idea of a confidence interval. So I have this news headline: growing share of Americans say affordable housing is a major problem where they live. Go check the news story out. All right, amid these circumstances, about half of Americans, 49%, say the availability of affordable housing in their community is a major problem. This is up from 10 percentage points, it's up by 10 percentage points from an early 2018 study. Okay, so I want to learn a little bit more about where they came up with this 49%. We see these things in the news all the time, these claims. Hey, 49% of people believe this, 75% of people believe that. How do they measure that? Where do they get that percentage? They didn't ask me. They ask you? Probably not. Who did they ask? All right, so sometimes in articles like this, maybe at the bottom, maybe at the top, there'll be a little note about how they got that. Okay, so I see a note down here with a link to their methodology. So what was their method of attaining this information? So I go to their methodology page, and they say this was part of the American Trends Panel Survey. It's a national survey they conduct of US adults, blah, 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 blah. When it was conducted, 9,676 people were asked a variety of questions, one of which was, is affordable housing a major issue in your community? And they either said yes, or they said something else. And we can go see the exact question, what their options were if they want. Now, they also say right here, the margin of sampling error for the full sample of 9,676 is plus or minus 1.6 percentage points. What does that mean? So bottom line is, if we give some kind of statistic in the news, it's, again, an estimate of what's going on for the population. But again, they didn't necessarily ask everyone unless it was the US Census when they did try to ask everybody. So there's always going to be a margin of error. If there's not a margin of error with a statistic about a large population, then that statistic is probably crap. So what does that 1.6 margin of error mean? Let's take a look. So here's that statement: about half of Americans, 49%, say the availability of affordable housing in their local community is a major problem. All right. Now, what do we know? There's a sample that was taken, and we had a little bit of details about that sample. For that sample, the sample size N was 9,676 people were in the survey. And this 49% is a sample statistic. So P hat is what we usually call that. P for proportion, hat for sample is 0.49. And this is what we refer to as a sample statistic. And I'm using, or Pew is using, this sample statistic to estimate what's really going on in the population. So we're using this sample statistic to estimate the true population parameter. Let's see, I want to write true first. There we go. Let's get the letters in the right order, Gary. There we go. The true population parameter. So remember the difference between a statistic and a parameter. A statistic is something we measure from sample data. A parameter is something measured from the entire population. Generally, we don't have the entire population, so we have to use sample statistics to estimate population parameters. So now Pew claims that we believe that about 49% of Americans, all Americans, adults in this case actually, say that affordable housing is a problem. The availability of affordable housing is a problem in their community, a major problem in their community. Now, since they didn't ask everybody, there's a thing we can calculate called a margin of error. So I'm just going to draw a little number line to demonstrate margin of error here. So I have in the middle here of my number line, my P hat, which is that 49%, 0.49. Right, which we could also call 49%. Sometimes we state them as decimals, sometimes as percents. Now they claimed their margin of error was 1.6%. So what the margin of error does is it says, well, the actual number is somewhere in this window where we go plus 1.6% to the right, and we also go 1.6% in the other way. So we do a minus 1.6% to go that way. And this distance I travel on each side is what's called the margin of error. So if I add 1.6 to 49, then I'm going to get, what, 50.6% on that side. And we could also do the decimal version to that 0.49. I could add 0.016, right? That's 1.6% as a decimal, and that's going to give me 0.506 as a decimal version of that same number. Heading the other way, let's see, -1 would be 48, minus 0.6 would be 47.4 on this side. And I'm going to write that in blue for percent. 47.4%, or as a decimal, 0.474. So now, instead of just this point estimate here for the population parameter, so again, this is what I call a point estimate, I now have widened it to consider kind of any number in this region from one end all the way to the other. So the point estimate, the middle, the sample statistic, plus and minus the margin of error. And so this right here, the whole thing, that's supposed to be a curly bracket, is what we call an interval estimate. So what they could have said instead, based on the sample data, is we think somewhere between 47.4% and 50.6% of Americans say the availability of affordable housing in their local community is a major problem. So they actually have a window going on. But often in the news, we just state the point estimate, and if people want to read the details, they can do some research and figure out what the hell the margin of error is. And the margin of error matters, right? If the margin of error was like 30%, which means from 49, it could be 30% lower or 30% higher. So the actual proportion might be somewhere between 19% and 79%. That's a huge window, and it's a worthless estimate. So if the margin of error is too big, the estimate is pretty much worthless. So we usually want a relatively small margin of error, but there can never be a margin of error of 0 unless you have the whole population, and we almost never have the whole population. So this interval we're creating here, so my interval, in this case, stated in mathematical interval notation, would be parentheses 0.474, comma 0.506 in decimal format. And that's this range of numbers from there all the way to here. Okay, now, could they be wrong? Could it be the actual population parameter of Americans who say affordable housing is not readily available in their community is a major problem? Could it be that it's actually below 40.7 or maybe above 50.6%? It's like, yeah, there's always that possibility. So along with this, they also have what they call a confidence level. So let's see if we can figure out what their confidence level and what that means is. So we're diving a little deeper into percentages we see in the media. It's related to an idea called confidence intervals. And if I scroll down, eventually, I'm going to see, getting closer, data collection, weighting, getting there. Here we go. The following table shows the unweighted sample sizes and error attributable to sampling. And they say they are using what's called a 95% confidence interval for this. So what does that mean, a 95% confidence interval? I'll draw a picture of it and I'll show, make some statements about what it does and does not mean. So let's get a new page and draw that confidence interval on a number line. So here's my number line. And whenever we have a confidence interval, we have basically 3 or 4 big numbers, 4 big numbers we need to think about. What's the center of the confidence interval? So that's my 0.49. And then from there, what's the margin of error? So the distance from the center to the edge, let's call that ME for margin of error. In this case, it's 1.6%, or as a decimal 0.016. And so I add that to 4.9, that puts me out here on the edge. Choose blue for that. So that was that 0.506, 50.6%. And I also take it away on the other side. So I'm going to get a number equally spaced to the left, and that was 47.4%. Oops, extra point there. So 0.474. So the endpoints of the interval are important numbers, right? That's the confidence interval. The middle number, again, here is my point estimate. And in this case, it's a sample proportion. And then I have the margin of error there. Now, the 95% fits in here by drawing this bell-shaped curve. And I'll show why it's a bell-shaped. Ooh, pen slip there. Let's try that again. Bell-shaped curve. All right. And that was supposed to be centered. Boy, I'm having a hard time drawing today. Can I move you? Maybe. I'm trying to center it on that. Pen is not cooperating. Let's call it close enough. All right, so I was trying to center it on that point estimate in the middle there. And what the 95% means is that there's this collection of stuff in the middle, 95%. So think of this like a histogram. And remember our 2 standard deviation rule for a histogram, the 95% rule. So I'm trying to draw a normal type curve, this bell-shaped curve, where 95% of stuff is in the middle. And the question is, well, what kind of stuff is in the middle there, Gary? Good question. This type of histogram is called also a sampling distribution. And a sampling distribution is different than a distribution for a sample. It's a whole other idea we'll look at in a minute. And in particular, for this case, because I'm talking about a proportion, P, this is a distribution of sample proportions, more specifically. Distribution of sample proportions. And the theory for this distribution of sample proportions goes, well, let's imagine that Pew Research, the people who came up with this, they had their sample of size n equals 9,676. Let's suppose they did a new random sample of 9,676 American adults. And they calculate the percent of people who say, yeah, affordable housing is a major concern for me. And then there's the people that didn't say that, that's fine. And they do it again and again and again. And they do a whole bunch, many, many samples of the same size. And each time from those samples, all we care about is the percentage of people who said housing is a major problem in my area, affordable housing. And over again, they do that. And let's let many be 100 times here. And then what we would expect is if this was a good random sample to start with and the rest are good random samples, we would expect 95 of those samples to have a mean somewhere in this, or a proportion somewhere in this region. And we would expect 5% to be outside of that. So that would put 2.5% of the samples out here and 2.5% of the samples out there. But the middle 95% is going to be around this range here, 47.4 and 50.6%. That's the idea of a sampling distribution. It's a distribution of the proportions of a bunch of different samples. So I just want to show you that in action through a computer simulation. And to do that, I'm going to look at StatKey. So here I have a picture where I took their original sample of 9,676 individuals. If from the 9,676, if 4,741 of them said, yeah, I think a major issue is affordable housing in my community, right? We count them as yeses, and then the other 4,900, their answer is something else. That's the 49% right here, right? 4,741 divided by 9,676 is pretty darn close to 49%. Then what I do is I take all of those 9,676 answers were a yes or something else, and I put them in a hat and I shuffle them and I pick out of the hat again all of those numbers one at a time. I just look at it and put it back in, and that gives me a new sample. So for example, it could be that from all of these slips, 9,676 slips of paper in a hat, the next time I drew them out one at a time, looking at them, I found only 4,683 of them were yes to that question, and the rest were something else. And every dot on this grid here is a slightly different sample based on the original. And in this case, I found 95% of, I did 8,106 new samples based on the original. 95% of them had a sample proportion to that question that ranged somewhere between 48% and 50%. Okay, kind of near the 47.4 and 50.6% I saw before. I'm just going to reset and just show it again. So again, in a hat, I put 9,676 pieces of paper, computerized hat. 4,741 of those papers say yes to the question, the rest say something else. And then what we do is we have the computer pick out of the hat 9,676 times. So I'm going to hit generate one sample. So it resampled the 9,676 people, and this time found, based on the original, only 4,687 said yes to that question. And if I resample again from that hat, generate another sample, I'm going to get a slightly different answer, and those are the dots down here at the bottom. And every time I generate a new sample of size 9,676, I get a slightly different answer. The third one I got was over here, where I get about 49.2% of people said yes. And I can do this over and over, generating these new samples, and it's going to make new dots on my dot plot. Now, instead of just doing it one at a time, I could do it 100 at a time. And each time I resample, I'm going to get a slightly different answer. And each one of these dots represents a different answer. Like that one right there got 48.4. And this one over here got 50.3% of the vote for that question. Why do it 100 times when I can do it 1,000 times, or 1,000 more, and 1,000 more? So I'm building a sampling distribution. So I'm having the computer simulate, based on the original sample, the idea of taking another sample of the same size. So at this point in time, I've made 6,107 samples. Each sample had 9,676 individuals based on the 4,741 yeses. Kind of complicated, but this is the idea of a sampling distribution. And if we do this enough times, we should end up with this bell-shaped histogram. Right? So this is that bell shape I was kind of sketching out before. And if I do that 95% rule, where I just hit the two-tail button there and ask the computer, figure out where the endpoints would be if 95% of the samples I took, those 8,107, are in the middle. So the computer says, okay, of all the samples we just redid, the middle 95% have proportions between 48% and 50%, consistent with what I did last time. So this is a way to create a confidence interval. So based on that sample, I could write back to Pew and I could say, well, computer simulation shows a margin of error. What's the margin of error? The margin of error with simulations, the best way to calculate it is find the distance across the interval. Oops. So from that 48% to the 50%, 50 minus 48 is 2%, and then cut that in half. The margin of error is the distance from the center to the middle, but sometimes these computerized ones are a little off center. So we always have the length of the interval. So max minus min over 2 gives me a 1% margin of error. So I could write to Pew and say, hey, I think the margin of error is more like 1%. And they would say, well, we have a slightly different technique that says the margin of error is 1.6%. 1.6%, 1%, they're similar. So again, what's the idea? Anytime we see these estimates in the news about the average person makes this much money, or this percent of people believe something, it's never 100% true. They usually base it on what we call a 95% confidence interval, which means the real answer they think is in this range of numbers here. Now, are they 95% sure they're correct? No, that's not what the 95% means. What does it mean? Let's write that down. So what does the 95% mean here? What does it mean to be 95% confident in an estimate like this? Question mark. What it means is that 95% of similar samples will have an interval, right? Because based on a particular sample, I can calculate the center and the interval for that. So any sample I'm taking, I can find that interval. And 95% of any possible sample you could make will have intervals that actually contain the real population parameter. So 95% of similar samples will have an interval that contains, whoa, crazy pen. The population value, the population parameter. Okay, so here's the problem though. I don't know if this particular sample is one of those 95%. Right? I'm hoping it is. I'm hoping the actual percentage of Americans who believe this is somewhere between 47.4% and 50.6%, but you never know if your interval actually contains it. There's a 5% chance that my interval missed the actual proportion, okay? So is there a 95% chance my interval is right? No, not really. There's a 95% that similar samples will make an interval that contains the actual parameter, but we never know which one is which. That's life. That's what it means. That's the introduction to confidence intervals with proportions. More later. Thanks for checking this out.